Okay. So, hello everyone. Thank you for inviting me. And here I'm going to talk to you about the work we have done in FMI in improving wave forecast in the Baltic Sea, with a special focus on the Gulf of Finland, of course, and the statistics that we have developed trying to create more and more useful products for the people working at the sea, so that they can use our products well. As this is Gulf of Finland Science Days, I thought it would be fun to start with small facts about Gulf of Finland. This is a very narrow basin that is very limited in the wave growth due to the shape of it. However, it still has very high wave heights in some locations. For example, just a month ago, Estonian wave buoy measured 5.8 meter waves in the western half of Gulf of Finland. But because this presentation is about wave models, I thought it's fun to show you our forecasted model situation here. The extreme value was measured in that X location there. One other fun thing in Gulf of Finland is that the other extremes that we have measured at the Gulf of Finland wave buoy, 5.2 meters, they have occurred in completely different situations, one with easterly and one with westerly winds. So both directions can cause quite high waves in the area. But this is not really the topic of the presentation, so let's go to the main thing. In FMI, we have these two main focuses of the developments on the waves. One is this basin-wide scale that we do together with PALMFC Consortium. It's this Copernicus Marine Service called Baltic Monitoring and Forecasting Center, where we, together with Danish, Estonian, Swedish, and German colleagues, developed the ocean models and forecasts in the Baltic Sea region. And big main focus on the wave side right now here is the coupling of the ocean, of our forecast to the ocean ice model to represent the sea state as accurately as possible. And on the other side, in FMI, we are focusing on improving forecast in coastal archipelago areas, as these are very unique and complex locations in the scale of the whole world. Previously, this work with the archipelago has been focused on the archipelago sea area and the coast of Helsinki, but recently the focus has shifted more towards the more tailored products at the fairway locations. When you think about these two developments in the point of view of Gulf of Finland, then we know that Gulf of Finland is seasonally ice covered, as mentioned before. It occasionally has strong currents and a large chance of the sea surface height variations. And all of these are something that we can get from ocean ice model and include into our wave models to get a bit more accurate results, possibly. And then again, especially the northern half of the Gulf of Finland has very irregular coastline and rugged bottom topography and lots of islands. In the right side, you see the bathymetry used in this fine resolution Helsinki model and the results coming from that. And in the left side, there's a picture of how the wave heights waves have accumulated to the certain areas due to the bottom topography in the archipelago sea region. And this kind of information can be very important for shipping safety or structures if you put, for example, wind power plants into the sea. But the main topic of my presentation is in this basin scale approach, so the coupling between the wave and ocean models, as this is what I have worked myself more with. Currently in this PALMFC system, we are running separately this ocean ice model, NEMO SI3. This SI3 is now the IceCamp part, and I don't know the nicer name for it. And then the wave model VAM. They are both forced with the same atmospheric forcing, and then NEMO and VAM are exchanging information with each other offline. Currently, our wave model reads in ice currents and sea surface heights from NEMO, and then NEMO reads in Stokes-Coriolis forcing. And We are right now working on implementing this sea state-dependent momentum flux to our system. However, this is a bit larger task and will require online coupling, so it won't be happening in the next year, or maybe not even on one after that. I thought that I would go through each of these couplings and how they have affected our wave model forecasts. First, we'll start with ice, as this is the single most important factor out of these three that affect the quality of the wave forecasts in the Baltic, as the location of ice affects the areas where the waves can grow. And the most accurate product that we have right now available about the ice conditions at the Baltic are these shear charts that are produced by the ice services in FMI and SMHI. And we use these often when we do analysis back in time, trying to see how the current wave situations have been. However, when you think about making long forecasts, for example, up to 6 days in the future, like we do in the BALMFC, then these stationary ice fields might end up being very wrong. And then using ice information from the 3D model might be a better approach, even though these models tend to overestimate ice a bit right now. However, they have added the assimilation of ice to our next product, so I'm expecting that to get better. It's going to be online at the end of this month. So, other side of this are the sea surface currents that we added to the system a few years ago. Overall, the current-induced difference into the wave fields in Baltic Sea is very small. As you know, the currents in the Baltic in general are small, but in some storm situations they can grow to quite large values. And in here, we show you one example of the situation where adding a current field to this wave model has actually improved the model results in Gulf of Finland. This spectra shows the measurements at the Gulf of Finland wave buoy, shown in the arrow in the right. And here we had the strong currents in northern half of Gulf of Finland, and they refracted the long wave as well towards the Estonian coast. So even though these situations are rare, it might be important to take this kind of refraction in account when you think about, for example, coastal structures that are very sensitive to the longer waves, for example. Most recently, we added also sea level variation to the wave model. Same story as with the currents. In general, the effects of sea surface heights on waves in the Baltic Sea is small. However, in coastal regions where we have very shallower areas where the waves actually interact with the bottom, because as the point of the view of the waves, Baltic Sea is still very deep sea in many areas. But in this picture, I show you the largest increase that we saw in the significant wave height and the smallest increase. That's very empty figure, I know. I was wondering why did I even put it here now yesterday when I looked at it. But from this you can see that sometimes when we have higher sea levels in the, for example, at the end of the Gulf, we might get even 1 meter higher waves in the regions where we have very shallow areas that have. Yes, so this kind of approach might be very important when thinking about these extreme cases and the safe sea level or safe building levels in the sea. Now this is what we have done with the wave model, and let's move to the ocean side of the things. We have implemented the Stokes-Coriolis forcing to the NEMO model, and this is the same story as before. The effects are only happen when we have a very stormy conditions, where you can actually see differences in the model system. This case is even less often than with the waves. And I must say that one of the reasons why this is added is also that in the Copernicus we want to have very similar models all around the Europe, and the seas are very different. So sometimes we need to add things that don't really make much difference. In this figure, at the very peak, you see the difference caused by the Coriolis forcing in the system. So currently we are working on this sea state dependent momentum flux. And the thing here is that currently the NEMO calculates shear stress felt by the sea using only atmospheric forcing and does not take account of the sea state. But in the coupled system, the situation would change so that in areas where the waves grow, the ocean model will experience less stress, and the areas where the waves will be breaking, for example, the ocean will see the more stress. So the area where the ocean feels the stress will shift and change. So this is actually causing quite large differences to the wave model. In these pictures, the red values are the ones that have the stress parameter in them, and the bluish-green values are the ones with the Stokes-Coriolis or just nothing in them. So you see the difference is quite huge. There's time series of 2 different locations, and if you look at the one in Hamina, it looks that implementing of this stress parameter actually makes everything much worse. But this is actually more of a tuning issue, as these models have been made to... the main thing of these models is to get the sea level variation correct, as is very much needed for the shipping. And but in the lower figure, you see that during this same event, when we did over and undershoot the sea levels a lot in the Gulf of Finland, we did actually manage to get the sea level better in the Warnemünde region. That is a bit more challenging. So this gives us hope that this might not be a useless task. And with tuning, it might actually give us nice correction to the whole system. So a little bit about the coastal modeling of the archipelago sea areas. As I said, we have now moved more towards this approach that we go into the certain fairways and work together with the pilots in that area to give them information they need. In this figure, a red triangle shows the location where pilots often embark ships. And as from the right upper right corner picture, you can see this is in this area you can still have quite harsh wave conditions, and they use our forecast to make the decision if they embark the ship or not. And in point of view of me at least, I sometimes just think that, well, big values, high waves, that's the problem. But actually, when talking to the pilots, we have learned that in this area, for example, it's challenging to the most challenging conditions come with the waves coming from the south, as they go from shallow regions and they're very steep, even though they're not very high. And so we are now working towards taking account this kind of information when we provide products to the ships and the pilots there. On top of these forecast products, we of course calculate the different statistics of the waves, helping people to make decisions on spatial planning, on structures at the sea. This is a picture of a traditional statistics, for example, percentiles of the highest waves in the Baltic Sea, and they are very well known in Baltic in general. There has been many studies on this using different atmospheric forcings and so on, and we know that the seasonal variation of waves is very big and important in the Baltic. When we do these kind of products, we use this PAL-MFC hindcast product. It's a 1 nautical mile, 1 hour time resolution model that is available for everyone, and we are updating it every 6 months from now. And because I'm now here, I have to advertise to you that we are gonna update this product next year, using a new version of VAM that is going to be using ST4 physics. So this is a new source term package of parameterization of dissipation, but parameterization for dissipation of infinite waves. It's actually not that new, but still. And we have seen that, for example, in Gulf of Finland, in the scatter plots, we have been able to produce better peak periods, in the Gulf, at least in the Gulf of Finland wave buoy location. Left is the old and right is the new. So wait forward for that, it's gonna be nice. And it's also gonna cover almost 20 more years of data. But more about the statistics that we have been calculated. Together with Natural Research Institute, we were trying to estimate the areas where we could have more fish farms in the coast of Finland. And we did this by looking at the areas where the wave conditions are mild enough, often enough. And this first approach that we had was that we calculated the percentage of days when the maximum significant wave height was below the certain threshold, and then looked at the areas where they were below the certain threshold often enough. For example, for feeding, the significant wave height was okay to be only 1 meter per second, 1 meter, and they had to have that at least 70% of the time. The feeding season, or the growth season of the rainbow trout in this case, was from May to October, and as you can see, the October is actually the limiting factor here, and it's also the time when they have to get the fish out of the sea. So they have to do this harvesting and placement too, that is 0.3 meters. So it's quite challenging in many areas of the Baltic Sea. However, this approach is quite crude. It's not maybe a problem if the significant wave height goes over the threshold for a few hours, because the rest of the day you still can use. So then we started to look into this more detail, and calculated this event-based wave statistics. This is a similar approach that is used in the point measurements very often. You just give a threshold and look how often that is exceeded and for how long. And as you can see, from giving a different threshold, you get a very different point of view of the things and the number of the events. But for example, in the point of view of the fish feeder, it wouldn't matter if the waves went all the way to the 4 meters. If it was still over 1 meter for 13 days, they couldn't go to the sea. So we calculated this kind of statistics for the area of the fish farm that they have in the Botnian Sea. And in the right figure, you see the number of the events during this growth season over this area. And in the orange triangle, you see the location where they have fish farm right now, or that is currently set to be okay location. And this blue is 20 kilometers offshore. That is area of interest that could be put fish farms also here. And then we calculated, looked into this situation more in detail, looked the number of the events in different locations, and as you can see, the number of events double if you go 20 kilometers offshore, and the percentage of time that's a significant wave height was over 1 meter in October changed from about 25% to closer to the 50%. We also looked at the distribution of the event lengths, so that people planning their structures would have this information of how long the events also last in general in the locations. In the inner location, 20% of the time events were higher than 27, last longer than 27 hours, but then again in the outer region, those 20% of the time the events lasted over 36 hours, so 1.5 days, so that's a big difference in the system. We also calculated the same kind of statistics for the entire Baltic Sea, using at the warning levels. We have 4 significant wave heights for shipping, and in here you can also get the information about how long these events in general last. In the lower figure you see the median duration of exceedance of different thresholds, but you can also take the maximum or minimum percentile or whatever out of this information. So, to summarize, in FMI we have been developing wave models both in basin and coastal scale, and we have been trying to produce more and more useful, tailored products of statistics for our users at the sea. Development of a coupled ocean ice, wave ocean ice model has shown that inclusion of currents and sea surface heights has improved the forecast in some high wave or high current or sea level situations. And we are currently working on adding this sea wave parameters to the ocean models to possibly even more greatly improve the results in the area. Not necessarily straight away giving a better results, as the tuning is very much needed, as you saw. Our developments in the coastal modeling have made it so that nowadays we have improved our forecast nearshore so that people can actually use them close to the coast, even in the more archipelago-ish areas. And we have been giving more and more tailored statistics to maritime traffic and different offshore activities, so that they can not just think about the level of stress that structures can feel, but also take into account the maintenance procedures at the sea. So thank you for your attention.
Thanks a lot for also being so compact and concise. Questions?
One question about the fish farm and the Gulf of Finland. About the fish farm.
Yeah.
So, because I know in Norway they are making big offshore structures. They have to have higher wave height than 1 meter. So can you decrease the wave height by engineering structures or somehow?
Repeat.
Lots of investments done in Norway, for example, inside the
Repeat the question for audience.
Not maybe a topic area, but anyway,
Yeah.
my question is that 1 meter is very low to me.
Yeah, so if we can increase the level of maintenance from 1 meter to higher, I think that's very possible by, for example, having different ships to do the maintenance. But often the fish farms don't have that kind of funding in Finland like they have in Norway. But that is very true that this very low threshold we might be able to increase them, especially if we can show that there's no places where these low values actually exist, or enough of those. They have a lot of money. Yeah.
Some more questions? Yes, please. Over there, yes.
Me?
Yeah.
Yes, thanks for a very interesting presentation. One of the first slides you showed the waves in front of the sea ice, and some of them were getting very high. So how come that the ice controls that much of the wave height? Could you elaborate a little bit on that? Yes, that's...
Well, these very high waves, they have come from winds coming from the south. So in those regions we didn't have ice. And when we hit the very dense ice field, it dampens waves very quickly. And was that your question?
Yes, so how come that there are these very high waves in front of the sea ice? Is there some sort of dynamics between the waves and the ice particularly causing the waves?
Well, there definitely is. Our wave models work so that they simplify the situation a lot. So when we have ice information from the model or forecast, and where the amount of ice is high enough in the concentration, like over 30%, then we should say that there's no waves at all underneath the ice, even though in reality they do interact with each other, and it is a very important development step to the wave models.
So basically the problem is the specification of where the ice is. In this case, waves are coming from the south, and the high waves on the left picture, just because the model tells there is no ice in this region. So ice almost completely damps waves, but the question is where the ice is, which is not known in the modeling time.
Thank you.
So how realistic can it be?
How realistic? These ice charts are information based on the satellite images, so they are quite realistic for that time, but they do not change in time. And the ice models themselves, they do tend to overestimate the ice, so it's not that realistic anymore, but it's work of development.
Just reminding the sentence of George Box, all models are wrong, but some are useful. Juha, please.
May I comment on this? I have been with Aranda in a situation exactly like that. And the entire Bothnian Sea, it's a very long catchment area, so you get very big waves in there. And also, just before the quark, there's a deep area, so the waves can really form, and then as it shallows up, they get really high. And just like the reality against the model here shows that it eats at the ice edge quite effectively. And actually, when you're in the slush, the broken ice, you have huge waves going on many nautical miles into the ice. And we have been in there with Aranda doing ice measures, and it's actually quite scary. It's an awesome situation, you know, middle of the night, the ship's searchlights on, and you can see this ice field go like that, ship rolling about and everything. I think this is a very good illustration of the fact. Another thing, question concerning the fish farms. Have you considered the currents on the bottom in different conditions, since that is actually also very, very important, since it carries away the nutrient loading from the fish farms, and it's actually in a situation where you dampen the waves or do any construction in order to achieve that, you might actually end up in a situation where there's a kind of a stall on the bottom and everything accumulates.
Oh, good point. I think we definitely should look into that, but we haven't yet. Yeah.
Yes, please, and please wait for microphone. Or you have one?
I have
yes,
it
very
already.
good, thank you.
Thank you very much. It's a very interesting presentation. My question is, when you look at the coast of Gulf of Finland, as you said, it's a very irregular coastline and it's very rugged. Yeah. So how do you predict the waves behind or those islands or archipelagos, like really close? Do you need, for example, phase-resolved models in coupling with the larger model like WAM? Or like, is there a strategy to go really close shore?
Well, one strategy that we have with the archipelago, with 1 nautical mile models, is that we use these obstruction fields. So we tell the estimates of how much these islands might dampen the waves and then weaken them, and we do that in both X and Y direction. But if we go to the more final scale models, then we don't have to use them always. Although we don't have resolution fine enough to resolve all of our islands anyway, so we always use those obstruction fields.
Right, yeah. Because kind of in contact with your colleague at the Norwegian Institute of Meteorology Institute, like Jan Victor and Konstantinos, we think about like a downscale cascade modeling that's when you go really close to the coasts and have irregular coastline, you can couple the WAM results to a phase-resolved model in a small scale for maybe even phase-resolved forecast. So that's also, I think it's kind of, can be the future, also good for safe navigation, kind of can collaborate over there. Just a comment there. Thank you very much.
Mm-hmm. Thank you.
Any more urgent or even worse burning questions? I think a lot has been done, as Hedi was telling, but there is still a lot of opportunities and challenges. What can't be done in models, statistical models or WAMP-type models, even very high resolution, is a production of refraction in archipelagos. So the patterns of waves are no more simple wave crest. You will have a lot of pyramidal waves behind small islands and shoals, etc. And then you probably need experience from Norway to build phase-resolving models in critical places, just not to lose small boats who are going to hide themselves behind small islands, which is actually a very deadly exercise, I would say, to be in a crossing wave system behind a small island. So thank you once more for a very nice presentation and giving a clear picture where we are and also depicting some challenges what we have. Thanks.
Thank you for